Okay, welcome back. We're on page 338. We're finally done with Turing machines, and now we're start talking philosophically about the non-deterministic polynomial time. What is an NP problem? Okay, so we've talked about the big O right over and over again. So big O is typically expressed as a polynomial, right? That's how, like n squared or something like that, right? So if I'm doing like matrix multiplication, it's going to be a rather large number, right? So if I pop over here and say, like n cubed, dang it, is what happens if you do matrix multiplication using the standard technique. That's a hockey stick. I mean, that's going to go very, very high. But it is something you can calculate, okay? So the idea is that these are what's called polynomial time. It's sometimes called a tractable. It's tractable, which means I have a formula. I can figure it out. I mean, I can go in there and figure out, if I add more work to my thing, it's going to behave such and such. And then there's another class of problems. The P class of problems are the ones we've been doing up to now. And there's an NP class, a non-deterministic polynomial time, an NP class problem, which are called intractable. Hey, what's the definition of intractable? So intractable basically means difficult, hard to deal with. Okay, so an intractable problem is one that's going to be difficult. Okay. So what that really means is no algorithm can solve this in a reasonable period of time. And just put reasonable in quotation marks, okay? So these are considered non-deterministic polynomial time. So an example of not reasonable, okay, is something like this, where if I said O sub n factorial, okay, that is about as much of a hockey stick kind of a thing. That it's going to hug the y-axis really tight. So if that is your solution, then wow, that's just barely something that you can deal with, right? And it should be fairly obvious that if you had lots and lots of data, then if the big O notation was that, and you had millions of rows of data in your database, and you tried to run something like that it could quite frankly take 50 or 60 years for it to process. So that would be, right, an intractable problem. Okay, just saying. All right. So one more time. So here's an easy one to get your head around. Let's say you've got a stopwatch and you're doing something, and you got 10 items, and you stopwatched them, and it took 1,000 seconds to do 10 items. And so you say, great, and I put 11 items in there. And then it comes up and it says it's going to take 200,000 seconds to process that. It's like, wow. Okay, so all I did was add 1 unit of work, and instead of it, having some modest amount of effect on the performance, it has a huge detrimental effect on the performance. So much so that you could tell if the numbers got really, really large. Instead of going from 10 to 11, I went to 1,000 or something. Then the amount of time it would take would the sun would burn out before you would get the answer. Okay, good. All right, so a small increase in time for a small increase in input, well, that would be a normal polynomial time. But a huge increase in time for a small increase in input, that would be a non-deterministic one. Okay, remember, non-deterministic basically means I don't have the information to be able to really predict. I mean, my predictions are really, really bad. And I really need some more input before I can tell you what the answer is. Okay, so the way you solve a typical NP problem is like the example I gave with trying to crack a password. The typical technique is 2 parts to it. First part is you take a guess. Second part is you check to see if the guess is correct. And then you do it again and again and again. And how long is that going to take? Oh. Okay, so let's do another one. let's do the search for password length. Versus complexity. So here's one for estimating password cracking time. And there's a little chart that should basically tell you that if you only had 9 characters, it would take 5 days. If you had 10, it would take 4 months. If you had 11 characters, it would take a decade. If you had 12 characters, it would take 2 centuries. So you see how adding 1 character in the length makes this thing just explode, okay? So clearly this is an NP style problem. Okay, good. All right, so let's continue. So if somebody said, well, how many times am I going to have to guess? I said, you know, I can go in and tell you that the maximum number of times you'd have to guess would be 12 factorial, okay? Well, that's not exactly 12 factorial. It'd be the number of characters in the set, like 256 characters in a set, you know, to the 12th power. That, you know, it's a lot of math. Anyway, bottom line is, I can tell you what the maximum would be, but how long is it going to take me to get there? You know, maybe you're lucky. Maybe you'll get it on the first try. Not likely. So there's some work needed to determine what the maximum number of tries is. But to tell you the truth, why bother? Right? Knowing the maximum number isn't going to help you any. So you might as well just go ahead and get started. Okay. So let's talk about some real-world examples that are not password cracking. All right, here's an example called the traveling salesman. Okay. Now this one is tough to solve. Here's the scenario. I've got a map like we had. Remember we were doing the closest, you know, the closest path kind of a thing, that kind of shortest path kind of a guy. So I want to start here, and I want to go to these 4 locations and return using the shortest amount of time. So your mailman or your FedEx delivery guy would benefit from this because they all have a starting location, and then they make their route, and then they turn around and come back. And so wouldn't it be cool if they could look at the map and figure out the most optimal path? I go to this address, followed by this one, followed by this one, followed by this one, and then my return trip, and so I'm reducing the amount of time it takes, the amount of gas it takes, and all the rest of that stuff. That's a really cool problem. Okay? So you could visit all of the cities in any particular order until you found the one that would get you the optimum solution. You could. But did you know that with the current computing power, if you did that, most likely the amount of time it would take to produce the optimum map route to take would take longer than it takes to drive the route. In other words, if you got your assignment at midnight, okay, and your truck leaves at 6 o'clock in the morning, you only have 6 hours to be able to produce this map, okay? It's going to take you, I don't know, 8 hours to drive. Most likely it's going to take like 12 hours to produce the answer, and so therefore it's useless to you because you had to have already got on your truck and left by that time. So you don't have enough time to come up with the correct answer because this dang thing takes forever to do, okay? So it is a difficult problem. So look, here's something you're really going to have to wrap your head around. All right, the traveling salesman problem is not the MST problem, okay? It's not that, and it's not the shortest path problem. And you're thinking, why isn't it multiple spanning tree? Isn't that what we're doing? Well, let's go over it. Spanning trees just between 2 nodes. I'm sorry, shortest path is just between 2 nodes, okay? So if you just assumed, I'll just start from the warehouse and go to the closest one, and then the closest one to that, and the closest one to that, and the closest one to that, just do a multiple series of shortest paths, is that going to be optimal? No, it's not. And multiple, spanning tree, it fits them all, but won't tell you, it tells you how you can get to them all. But again, it's not optimum. It's not going to tell you which order to take to get there, because it's all about just getting from one place, hitting all the intersections, if you recall that scenario. Okay, so in Chapter 8, the MST cannot, we talked about that guy, but it really can't. It can't find the optimal path. Okay. So how do you solve this problem? Well, you generate a list of addresses you want to visit, okay? And that's typically going to be polynomial time, however you producing the list. Okay, just producing the list, nothing more. So if I had 8 addresses, that'd be big O sub n, right? Because I'm just producing a list. So what are the XY coordinates, so to speak, for each one of the things it's going to take about? And then generating the cost between each city. In other words, between each one, what is the distance between each one? And again, that would be polynomial time. So this problem has 2 polynomial time components. And then do it again for every single combination. Ooh. Every combination? Wow. Okay, now you've gotten to non-deterministic polynomial time. Now you've gotten, so most likely this can't be done in a reasonable period of time. So it starts off being kind of simple, producing a list, figuring out the cost between each one of the addresses, and then doing it again over and over and over and over and over. Wow. Okay. So that'd be an NP class problem, the traveling salesman. So on page 341, they talk about the problem reduction. This is kind of sort of important because it is possible to reduce a problem down to separate out the NP part. So the idea is reduce the problem to make it more simple. So if you can transition, if your transformation is in P class, and it can be reduced to P class, well then it no longer is an NP problem. You've broken it up, and each one of the components are in the P class, well then you're done. It's no longer an NP problem. You can move on. So let's give you an example. Let's say that someone has a list of Boolean values, all right? So the first part of this thing is going to be return true if any one of the Boolean values is true. Otherwise, return false, okay? So that's the first part of this thing. So I have an array of Boolean values. I just need to go through the array and one at a time, and then tell you whether or not if I run across any of them that are true or false, whatever, and then return. Okay. Part 2 is I need to figure out what the size of this array is, because just like mowing the grass, when somebody says how long is it going to take to mow the grass, you go, I don't know. How big is your yard? How long is it going to take you to go through the list of the array? It's like, I don't know. How big is the array? Okay. So return the largest value, or the size of the array. And so for sake of argument, let's say that you can do part 2, but you can't do the first one. Okay, just forever. So we reduce the first problem to become the second part. We've got it so that we've converted one of them, but not the other. Okay, just saying. Okay, so is it still an NP problem? I converted one of them, but I didn't convert the other. Well, yeah, it's still an NP problem. So on page 342, they talk about the NP complete, and basically what that means is that NP complete means that we currently don't have any P-type solutions that would work. Now, that doesn't mean that maybe sometime in the future we might, but we can't really be translated to anything else. That's basically what that means. Okay, we're coming up on the 15-minute mark, so this would be a good place to stop.